Good day. For those of you who don't know me, my name is Douglas Harder, and in this topic, we're going to be discussing solutions to systems of linear equations with backward substitution. So in this topic, we will focus on augmented matrices that are in row echelon form. We will determine if the system of linear equations associated with such a matrix has no solutions, one unique solution, or infinitely many solutions. We will examine the algorithm to find the unique solution if only one solution exists. We will introduce the concept of free variables, which we will use when there are infinitely many solutions, and we will examine the algorithm to find all solutions when there are infinitely many solutions. Now, suppose that the augmented matrix corresponding to a system of linear equations is in row echelon form. To remind you very quickly, row echelon form means that each subsequent row has at least one more additional leading zero, and all zero rows are at the end of the matrix. In this case, we will see how to determine if there are no solutions, one unique solution, or infinitely many solutions. And if there is either one unique solution or infinitely many solutions, we will describe how to find it or them. Now, suppose the augmented matrix is in row echelon form and the rank of the matrix A is not equal to the rank of the augmented matrix. If this is the case, then it must be true that the last non-zero row of the augmented matrix is of the form all zeros except for a non-zero entry in the last column. But this is the same as saying 0 times every single unknown added together is equal to a value that is not 0. This is impossible. And so therefore, in this case, no solution exists. Now, if the augmented matrix is in row echelon form and the rank of the matrix A equals the rank of the augmented matrix, then we are guaranteed at least one solution exists. We will see how to differentiate there being one unique solution and there being infinitely many solutions. Now, if the matrix A is m by n, meaning there are m equations and n unknowns, and the augmented matrix is in row echelon form, a unique solution exists if and only if n equals the rank of the matrix, which equals the rank of the augmented matrix. We will find the solution with backward substitution. But first, let us recall, if the rank is n, then there must be n leading non-zero entries. If there are already n columns in A, then because the matrix is in row echelon form, each column must have a leading non-zero entry. After all, we saw that if a matrix is in row echelon form, no column can contain the same number of leading non-zero entries. Thus, the only possibility is for A to be an upper triangular matrix with no non-zero entries on the diagonal. For example, here we have a system of two linear equations in two unknowns, and the matrix A is 2 by 2. The augmented matrix is in row echelon form, and the rank of A equals the rank of the augmented matrix. As we can see, the matrix A is upper triangular with no zeros on the diagonal. Now, let's examine the last line of that matrix. That last line says that 5 times x2 is equal to negative 6.5. Well, that's just a linear equation in one unknown, which you already know how to solve for. Divide both sides by 5. Therefore, x2 is negative 1.3. Now let's look at the previous line. The previous line says that 3 times x1 minus 7 times x2 is 4.3. All right, not a problem. But we know what x2 is now. x2 must be negative 1.3. So let's substitute in x2 into that equation. All right, so now we have this formula here. Now, negative 7 times negative 1.3 is positive 9.1. So we can subtract 9.1 from both sides. That gives us this equation. 3 times x1 is equal to negative 4.8. But that again is a linear equation in one unknown, so we just divide both sides by 3, which gives us that x1 is negative 1.6. Thus, the solution vector is negative 1.6, negative 1.3. Now, you can check this. Given this augmented matrix with the solution we found here, you can substitute those values into both equations and see that both equations hold. Alternatively, you can confirm that this specific linear combination of these two vectors on the left-hand side does equal the target vector on the right-hand side. Now, very quickly, is that solution unique? Is there another value of x2 that may allow this to be true? Well, no, there's only one value of x2 that may satisfy that second equation. Is there another value of x1 for which this may be true? And once again, you should be able to convince yourself if x1 was any other value, then in that case, x2 would also have to be different. But if x2 was different, then the second equation would once again not hold. So in this case, yes, I think you can convince yourself that there is one unique solution for this system of two linear equations in two unknowns. Here's another example. Here A is a 4x4 matrix. This represents a system of 4 linear equations in 4 unknowns. The augmented matrix is in row echelon form, and the rank of the matrix A equals the rank of the augmented matrix. Also, additionally, we see that A is indeed an upper triangular matrix with no zeros on the diagonal. Now, looking at the last line, this last row in the matrix says that negative 2 times x4 is equal to negative 3.8. So dividing both sides by negative 2 means that x4 is equal to 1.9. All right, let's go one row up. Looking at row 3. Row 3 says that 5 times x3 plus 8 times x4 is equal to 2.7. But we've just determined the value of x4, 1.9. So we can substitute that value of x4 into this equation. All right. 8 times 1.9 is simply 8 times 2 minus 0.8, which is equal to 15.2. We can subtract 15.2 from both sides. All right, what this now says is that 5 times x3 is equal to negative 12.5. And once again, this is now a single equation in a single unknown, and we can simply divide both sides by 5 to determine the value of x3. x3 is equal to negative 2.5. All right, so now we have found the values of x3 and x4. Let's carry on to row 2. Row 2 says that 4 times x2 plus 9 times x3 plus 7 times x4 is equal to negative 9.2, and we can substitute in the values of x3 and x4 that we've already found. All right, there we go. And we can now calculate that value and subtract that value from both sides. Consequently, we have that 4 times x2 is equal to, 0. Dividing both sides by 4 give us that x2 is equal to 0. So finally, going back to the first row, that first row gives us this equation. We can now substitute in the values of x2, x3, and x4 into this equation, which give us this result, and thus subtracting 3 times 1.9 or 5.7 from both sides, we get that negative 3 times x1 is equal to negative 1.8. Divide both sides by 3 to get negative 3 to get that x1 is equal to 0.6. Thus, our solution vector is this vector here. Again, you can check this. Given this augmented matrix with the solution vector shown here, you can substitute these values into the 4 linear equations and you will see that all 4 linear equations hold. Alternatively, you can confirm that this linear combination of vectors on the left does indeed equal the vector on the right-hand side. Now, for example, here the matrix A is 5 by 3. Again, 5 is greater than 3, and we see that the augmented matrix is in row echelon form and the rank of A is equal to the rank of the augmented matrix. So, the last 2 rows are 0 rows, and therefore we can ignore them. Consequently, we start at row 3. Row 3 says that 5 times x3 is equal to negative 4.5. Dividing both sides by 5 give us that x3 is equal to negative 0.9. Next, going to row 2, this says that 4 times x2 minus 2 times x3 is equal to 4.6. Substituting in the value of x3, we get this equation here. Consequently, subtracting 1.8 from both sides gives us the equation we see here. Now, dividing both sides by 4 give us that x2 is equal to 0.7. Finally, looking at row 1, substituting in both x3 and x2 into the equation defined by row 1 gives us this equation here, and calculating the constants and subtracting them from both sides, we get that 2 times x1 is equal to 1. Dividing both sides by 2 give us that x1 is equal to 0.5. Thus, our solution vector is the vector we see here. Consequently, this vector is the solution vector to the system of 5 equations and in 3 unknowns described by this augmented matrix. We can check this answer by substituting in the values of x1, x2, and x3 into all 5 of these equations, and you will see that all 5 of these equations do indeed hold. Alternatively, you can confirm that the linear combination of vectors on the left-hand side does indeed equal the target vector on the right-hand side. The backward substitution algorithm for finding a unique solution to a system of linear equations is as follows. If AB is an augmented matrix corresponding to a system of m equations in n unknowns where m is greater than or equal to n, and the augmented matrix is in row echelon form, and where the rank of A is equal to the rank of the augmented matrix is also equal to n, then we may proceed as follows. Start by assigning the variable k the value n. Substitute all values into the equation defined by row k that have thus far been determined. This is going to leave a linear equation in xk. Solve for that value of xk. Then, if k is now equal to 1, we are done. Otherwise, Assign k the value k minus 1 and return to step 1 in this algorithm. Now, the story so far. For an augmented matrix in row echelon form, if it is ever true that the rank of the matrix A is not equal to the rank of the augmented matrix, then the rank of the augmented matrix is equal to the rank of A plus 1. That means that the last non-zero row is an equation of the form 0 times each unknown all added together is equal to a non-zero value. This is impossible, therefore no solution exists. Alright, let us assume that A is an m by n matrix, meaning there are m equations and n unknowns, and the rank of the matrix A equals the rank of the augmented matrix, and both of these equal n, the number of unknowns. In this case, a unique solution exists. Now, for this to be possible, it is absolutely necessary that the number of equations is at least as large as the number of unknowns. Why is that? Because the rank of a matrix is the number of non-zero rows in a matrix that is in row echelon form. What this means is that every single row must have a different number of leading zeros. However, if there are fewer than n rows, the rank can never be equal to n. So the number of rows must be at least equal to n, if not larger. So consequently, can the rank of A ever equal the rank of the augmented matrix and have both of these values be greater than n? Well, this would be more or less impossible, because if the rank was greater than n, then recall that the rank of a matrix says that there are that many rows that have leading non-zero entries. However, every column can have at most one leading non-zero entry. Therefore, there must be at least as many unknowns as there are the rank of the matrix. This is therefore impossible to happen. Thus, the only other possibility is that the rank of the matrix A is less than n. Now, if A is an m by n matrix, meaning that there are m equations in n unknowns, and the rank of A is equal to the rank of the augmented matrix in row echelon form, and both of these are less than n, then there are fewer non-zero equations than unknowns. For example, x1 plus x2 is equal to 0 is a single equation with two unknowns. The corresponding matrix is 1, 1, 0, and we see that this is indeed in row echelon form. Problem: there are infinitely many solutions. For whatever value x2 takes on, if we let x1 be the negative of x2, then this is a solution vector to this system of linear equations. If x2 is 5, then negative 5 plus 5 is equal to 0. If x2 is equal to negative 3, then x1 is 3. 3 plus negative 3 is again equal to 0. Again, we see that there are infinitely many solutions. Now, looking at the augmented matrix in row echelon form, we note that if a variable is associated with a leading non-zero coefficient, this means that that variable or unknown can be written as a linear combination of all subsequent unknowns. So for example, Here we see an augmented matrix that is 3 by 5. It is in row echelon form. There are two leading non-zero entries, one in column 1, another in column 3. Now, what that first leading non-zero coefficient says that I can find x1 by subtracting off all other values from 8.9 and then dividing both sides by 7.6. Similarly, this second equation says that I can find x3 in terms of x4 by subtracting off x4 times the appropriate constant from the right hand side and then dividing both sides by 9.2. There are no such constraints for x2 or x4. Consequently, these two unknowns are going to be declared to be free variables. That means they can take on whatever values we want to give them. Thus, if A is an m by n matrix and the augmented matrix is in row echelon form and the rank of A equals the rank of the augmented matrix, which is less than n, then each unknown associated with a column that does not have a leading non-zero entry is a free variable. So for example, in this matrix, we note that these are the two leading non-zero entries. The first one is in column 1 and is therefore associated with the unknown x sub 1. The second is in column 3 and is therefore associated with the unknown x sub 3. Columns 2 and 4 do not have leading non-zero entries in them, and consequently we will declare x2 and x4 to be free variables. Now, if the augmented matrix is in row echelon form where A is an m by n matrix and at least one solution exists, then the number of free variables is n minus the rank of A. If the rank of A is equal to n, then there are no free variables and a unique solution exists. If the rank of A is less than n, then infinitely many solutions exist, and there will be n minus that rank number of free variables. All right, let's look at some examples. Here, the matrix A is 3 by 4, indicating that this is describing a system of 3 linear equations in 4 unknowns. The augmented matrix is in row echelon form, and the rank of A equals the rank of the augmented matrix, and both are equal to 2. The number of unknowns is 4, so 4 minus 2 is still 2, and so therefore there are 2 free variables. We will associate free variables with each column that does not contain a leading non-zero entry. So thus, x3 will be a free variable, and so will x4. In this example, I have a system of 3 linear equations in 2 unknowns, but the rank of the augmented matrix is 1, and consequently, there will be 2 minus 1, or 1 free variable. We will associate that free variable with the column that does not contain a leading non-zero entry, and that is going to be the second column, or x2. Here we see the augmented matrix associated with a system of 5 linear equations in 5 unknowns. However, the rank of the matrix A, which equals the rank of the augmented matrix, is 3. Therefore, the number of free variables is 5 minus 3, or 2. We will associate a free variable with the unknown corresponding to each column that does not have a leading non-zero entry? Well, the leading non-zero entries are 1.7 in column 1, 2.9 in column 3, and 3.7 in column 5. Thus, x2 will be a free variable, and x4 will be a free variable. Now, as an extreme case, here I have a system of one equation in 4 unknowns. The rank of the augmented matrix is 1. Therefore, 4 minus 1 is equal to 3. There will be three free variables. And there is only one leading non-zero entry. That's column 2. And so therefore, the three free variables will be x1, x3, and x4. As a first example, consider the system of one linear equation with 2 unknowns described by this augmented matrix. The rank of the matrix is 1, n is equal to 2, therefore there is one free variable. There is one leading coefficient, that is 2, and thus there is one column, the second column, that is not associated or does not have a leading non-zero entry. Thus, the variable associated with that column will be our free variable. So that will be x2. So that means we can solve for x1 in terms of x2. So this one equation says twice x1 plus 3 times x2 is equal to 4. We can subtract 3 times x2 from both sides, and now we can divide both sides by 2. Okay, so thus our solution vector is the vector 2 minus 1.5x2 with the second entry being x2. That means whatever value x2 takes on, we can calculate the appropriate x1 by just calculating 2 minus 1.5x2. So for example, if x2 is equal to 0, x1 is equal to 5. If x2 is equal to 1, then x1 is equal to 0.5, and so on and so forth. All of these are solutions to the linear equation 2x1 plus 3x2 is equal to 4. Now, notice that this vector can be written as the sum of 2 vectors, the one being just the constants, the second being 0, and the second being those that are multiples of x2. Consequently, the second vector is all scalar multiples of the vector negative 1.51. So, all solutions to the system of linear equation, well, it's a system of one linear equation, and 2 unknowns, 2x1 plus 3x2 is equal to 4, are all vectors of the form 2, 0 plus all scalar multiples of the vector negative 1.51. Now, top students are always going to ask, so I'm going to address it right now. There are alternative ways of coming up with a solution, but nevertheless, all solutions are equivalent. So for example, given the system of one equation in 2 unknowns here, if we were to follow the algorithm that I described above, we would let x2 be the free variable, in which case the solution would end up being this solution vector shown here. However, nothing prevents you from declaring x1 to be the free variable. And if x1 is the free variable, then you could solve that equation to find that x2 is equal to 3 minus 2x1. All right, so now we have 2 different solutions. Are they the same? Well, perhaps the easiest point to note is that the vector that is multiplied by a scalar in the first case is negative 0.51, and in the second it's 1, negative 2. you will notice that the second vector is a scalar multiple of the first vector. In fact, it's the first vector multiplied by -2. So, not a problem. But not only that, if in the second equation I take 0, 3 plus 1.5 times that vector, I get the first constant vector 1.50. So in fact, both of these solutions describe the entire collection of all solutions just in different ways. So yes, there are different ways of coming up with solutions. We are describing an algorithm, and once you have an algorithm, you can implement that algorithm in a computer. That is the point of an algorithm. We demonstrate the algorithm works, consequently, we can implement it in a computer. So, for example, let's take a look at this system of 2 equations and 3 unknowns. M is equal to 2, N is equal to 3, the rank of the matrix is 2, and consequently the number of free variables is n, or 3, minus the rank 2, which is equal to 1. So there is one free variable. There are one leading non-zero coefficient here, and here is the second. Consequently, the only column that does not contain a leading non-zero entry is column 2, and thus x2 will be declared to be the free variable. Alright, so let's start with the second equation with backward substitution. That last equation just says 5x3 is equal to 7, or dividing both sides by 5, x3 is equal to 1.4. Now going back to row 1, that says that 2x1 minus x2 plus 3x4 is equal to -6. Alright, x2 is a free variable, so it can take on any value we want, so we will bring that to the right hand side, and we have already solved for x3, so we will substitute that value in, and again also bring that to the right hand side. Consequently, this equation says that 2x1 is equal to -6 plus x2 minus 4 times 1.4. Simplifying the right-hand side and dividing both sides by 2 gives us that x1 is equal to -5.8 plus 0.5x2. All right, so our solution vector is this vector here, where x3 is 1.4, x2 is free, and x1 is the value we just found, which is in terms of the free variable x2. Notice once again, we can write this as a sum of 2 vectors, the first one containing just the constants, and the second containing any multiples of x2, and therefore we can factor out an x2 from the second vector. So, all solutions to this system of 2 linear equations and 2 unknowns are vectors of the form -5.8, 0, 1.4 plus all scalar multiples of the vector 0.5, 1, 0. Alright, let us consider this augmented matrix that represents a system of 2 equations in 3 unknowns. This augmented matrix is in row echelon form, and thus we can solve this using backward substitution. Alright, so we note that the rank of this augmented matrix is 2 because there are 2 leading non-zero entries. However, the number of free unknowns is 3. So n is equal to 3, and 3 minus the rank, or 2, is equal to 1. Therefore, there is one free variable. We will associate that free variable with the one column that does not contain a leading non-zero entry, namely the unknown x3. Alright, the second equation now says that negative 10 times x2 plus 11x3 is equal to negative 9. But x3 is free, so it can take on whatever value it wants. So let us solve for x2 in terms of x3. Bringing 11x3 to the other side, we get that negative 10x2 is equal to negative 9 minus 11x3. Dividing both sides by negative 10, we get that x2 is equal to 0.9 plus 1.1 times whatever value x3 is given. Alright, so we have now seen that x3 is free. We've solved for x2. Now let us go from row 2 back to row 1. Row 1 gives us the equation 20x1 minus 2x2 plus 7x3 is equal to 13. Now, we've found what x2 is in terms of x3, and x3 itself is free, so we can bring those onto the other side while substituting in what we found the value of x2 to be for x2. Alright, 13 plus 2 times 0.9 is 14.8, and negative 7x3 plus 2.2 times x3 is equal to negative 4.8 x3. Now, dividing both sides by 20, or moving the decimal place over by 1 and dividing by 2, we get that x1 is equal to this expression in terms of x3, the free variable. Alright, so our solution vector is now containing the values x3, which is the free variable in the third component. x2 is what we found it to be, 0.9 plus 1.1 x3, and the value we found for x1, which is 0.74 minus 0.24 times x3. Okay, now, writing this as a sum of two vectors, the first vector having just the constant coefficients and the second vector containing the term with x3, we get these two vectors summed here, and dividing out x3, or bringing x3 out of the second vector, we see that all solutions are of the form the vector 0.74, 0.9, 0, plus all scalar multiples of the vector negative 0.24, 1.1, 1. Now, before we get too far, let's make sure that everyone in the class understands what this solution means. Remember that this augmented matrix, which is in row echelon form, represents this system of two linear equations in three unknowns. The solution vector we found was that the values x1, x2, and x3 can take on any of these values, where x3 is allowed to be whatever you wish it to be. Let's actually examine that for the truth of that statement. So, for example, if x3 is equal to 1, then the vector 0.74, 0.90 plus 1 times that second vector is equal to the vector 0.521. Now, if we substitute those three values for x1, x2, and x3 into the first equation, we get that 20 times 0.5, which is 10, minus 2 times 2, which is 4, so 10 minus 4, which is 6, plus 7 times 1, so 6 plus 7, yes, that is indeed equal to 13. If we substitute those values into the second equation, we get that negative 10 times 2 plus 11 times 1 is, yes, negative 20 plus 11 is negative 9. So when the free variable x1 is equal to x3 is equal to 1, then the solution vector does indeed satisfy this system of linear equations. But we can let x3 take on any value we want. So we could even let x3 take on a value like negative 19. So if you substitute negative 19 into the solution vector for x3, you get that the solution is 5.3, negative 20, negative 19. Well, once again, let us substitute these values into the first linear equation. So we get 20 times 5.3, which is 106, minus 2 times negative 20, which is positive 40, plus 7 times negative 19, which is 133. So 106 plus 40 minus 133 is indeed equal to 13. With the second equation, substituting in x2 is equal to negative 20 and x3 is equal to negative 19, we see once again that 200 minus 209 is indeed equal to negative 9. And in fact, if you were to choose any other value of x3 that you want, even pi, and you were then to substitute those values into that linear equation, you would see that both equations are simultaneously satisfied. As a slightly more complex example, consider this augmented matrix that represents a system of 3 linear equations in 6 unknowns. The augmented matrix is in row echelon form, and as we can see, there are 3 leading non-zero entries associated with columns 1, 3, and 4. Because the rank of the matrix equals the rank of the augmented matrix, therefore a solution exists. However, because the number of unknowns, 6, minus the rank, which is 3, is 6 minus 3, or 3, therefore there are 3 free variables, and therefore there are infinitely many solutions. Let us try to find all those solutions. So, in order to do so, we need to first determine the free variables. We will associate each unknown, or declare each unknown that is associated with a column that does not contain a leading non-zero entry as a free variable. So, column 2 does not contain a leading non-zero entry, so x2 will be a free variable, and columns 5 and 6 do not contain leading non-zero entries, so both of these will also be free variables. So, starting with the last equation says that negative 2 times x4 minus 3 times x5 plus 2x6 is equal to 3. Let's bring everything other than the term containing x4 to the right-hand side. So, here we have this expression here, and now we can solve for x4 by dividing both sides by negative 2, which tells us that x4 is equal to negative 1.5 minus 1.5 whatever value we're giving x5 plus whatever value we give x6. All right, so now let's go back to the second equation. The second equation says that 5 times x3 plus 2 times x4 plus 9 times x5 plus 3 times x6 is equal to 2. Once again, let us bring everything other than the term containing x3 to the right-hand side. Now, we have already found x4 in terms of x5 and x6, so the first thing we do is substitute in x4 for the expression we just found. Okay, so now let's multiply out that expression to get, so multiply each term in that by -2. So we get now that 5 times x3 is equal to 2 plus that expression minus 9x5 minus 3x6. Well, 2 plus 3 is equal to 5. 3x5 minus 5x5 is -6x5, and -2x6 minus 3x6 is equal to -5x6. Easy enough. Now we can divide both sides by 5 to get that x3 is equal to 1 minus 1.2x5, whatever value x5 takes, that is, minus x6. All right. So we have found both x3 and x4 in terms of those two free variables. Now let us go back to the first equation. The first equation, again, describes x1 in terms of x2, 3, 4, 5, and x6, and let us bring everything to the right-hand side except for the term containing x1. So 2x1 is equal to this expression. Now, we've already found what x3 is with respect to the two free variables, and we've found what x4 is. So let us substitute both x3 and x4 into this expression. Now, with a little bit of work, we can expand those two expressions, and then we can collect all the constant terms, all the multiples of x5, and all the multiples of x6. Oh, and of course the multiple of x2. And so next we simply divide both sides by 2 to get that x1 is equal to -6 minus 1.5x2 minus 2.6x5 plus 7.5x6. Thus, we have found that given the three free variables x2, x5, and x6, we have determined the values of x1, x3, and x4 to ensure that all three equations are satisfied. Thus, we may write the solution vector as follows. Notice, once again, x2, x5, and x6 are free variables, and consequently they can take on whatever values we want. They don't have to be the same value. For example, x2 could be 7, x5 could be 582,221.5, and x6 can be 0. However, once we have chosen values of x2, x5, and x6, the values of x1, 3, and 4 are fixed. Notice also that we can write this solution vector as a constant vector plus all scalar multiples of these three additional vectors. Interesting, you will note that the only vector that has a non-zero entry in index 2 is the vector associated with the free variable x2. The only vector that contains a non-zero entry at index 5 is the vector associated with x5, and the only vector that contains a non-zero entry at index 6 is the vector associated with the free variable x6. We'll discuss more on this later. So, to write down the algorithm we've demonstrated in the last few slides, The algorithm for finding all solutions when there are infinitely many solutions is as follows. If AB is an augmented matrix corresponding to a system of m equations and n unknowns, and the augmented matrix is also in row echelon form, and where the rank of A is equal to the rank of the augmented matrix, and this is strictly less than the number of unknowns, then there are n minus the rank of A free variables. Declare any unknown associated with a column not containing a leading non-zero entry as a free variable. We carry on now. We start by assigning K the value of the rank of the matrix. So basically, go to the last non-zero row. Determine which variable x sub L is associated with the leading non-zero entry of row K. Substitute any values into the equation defined by row K that have already been determined, and this is going to leave us with a linear equation in x sub L and any free variables where the subscript is greater than L. Solve for x sub L. If K is equal to 1, we are done. Otherwise, set K to be the value K minus 1 and return to step 1. Interestingly enough, this second algorithm also works if there is a unique solution. The only difference, of course, is that there will be no free variables. Thus, in all cases, if there is a solution, the solution vector will be of the form of a fixed vector plus all linear combinations of a set of vectors, each of which is associated with one of the free variables. If there is only one solution, it is that one fixed vector. So, following this topic, you now understand that if an augmented matrix is in row echelon form, we can determine whether or not there are no solutions, one unique solution, or infinitely many solutions. We've also seen the algorithm for finding the one unique solution if indeed there is only one solution, and you've seen a few examples of that algorithm applied. You've also seen the algorithm for finding all solutions if there are infinitely many solutions, and once again you have seen that algorithm applied to a number of examples. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!